Well, hello and welcome, YouTube. It's Mr. Robinson's Q&A Power Hour, once again for Integrated Math 3. Now, Mr. Robinson's Q&A Power Hour is a series of videos where students ask me questions and I respond to them. Questions are asked and answered in the order which they're received, and they are content-based questions, normally on the last couple weeks of material, but as we're going into a unit test on polynomials and where we factor and solve them, I said I'd open the door for anything polynomial-based. Long as it's within the content, we'll go and cover it. Now, we have a good series of questions here. At least, I don't know what they are, but we have, I think, 16 or so of them. And there are actually two that I needed to add in the beginning that were from the last one that I feel like I needed to answer differently now that we've covered other material. So I am going to answer those ones first, again in a different light here, and I'll show you what those ones are in just a moment here. So, yeah, actually, let's just go ahead and pop them up right now and go straight into this. So the first two questions, again, were in the last Power Hour, and I need to provide kind of more different context now that we've seen a few different things here. So this first question, an old question, was, will there be a question that's not factorable? And this was asking about the quiz, but this was not what I cared about. But it was the, if something's not factorable, when there's no answer, is there any way that we could double check to make sure there's really no answer? Well, now that I've gone through a couple questions where we talked about complex roots and we're solving using the quadratic formula, one thing I kept telling my students that I want to go back to is, if you work the discriminant in your quadratic formula, let me go to it. If you work the discriminant in your quadratic formula in x equals negative b plus or minus the square root of b squared minus 4ac all over 2a, if you work that b squared minus 4ac right there, and if your value is a perfect square, a positive perfect square, or 0, I guess also works, then that means that your value was factorable. So let me do something that's factorable first. There was actually an example we had on one of our test things. Oh, one other thing I want to mention here is I also plan on making a video of what, my students did a pre-test before their test, and I ended up making a solution guide video for that test. So there might be questions buried within here that have to do with that. I don't know, but since they asked them probably after the pre-test, it's likely they might have questions based on it. So I might say wait for the pre-test for questions of that accord, or if it's general enough that I can cover it, then I will. Anyway, let's say we had something like 2x squared. I'll make it simple, minus, I guess, 3x plus 1. I think that works. If you were trying to factor, you're like, I don't know how to factor this. And I hope you kind of can now at this point. But what you could also do is do that b squared minus 4ac portion. And if this value, negative 3 squared minus 4 times 2 times 1, and that's going to be 9 minus 8, which is 1. 1 is a perfect square, right? And 0, 0, 1, 4, 9, 16, 25, 36. If those numbers are perfect squares, then the thing you're taking the square root of becomes a whole number. Therefore, they have rational solutions. Therefore, it was factorable. So if you weren't sure if something was factorable and you wanted to spend the time doing the discriminant, it's not long, but do b squared minus 4ac, you could actually check and see if your thing is factorable there. It doesn't tell you what it factors to. Right? Well, sort of. If you kept solving, you could kind of come up with them. But it tells you whether or not it's factorable. It's like those divisibility rules. Like, if something's divisible by 3, if your digits add up to a number that's divisible by 3, that doesn't tell you what it divides by. But it tells you whether it is, and then you can try it after. All right, and then the other question that was in this thing was, how would one factor a 5-term polynomial, if that's a thing? I think I was under the assumption at the time when it was asked, and maybe this was what they meant, that they were talking about factoring by grouping, and they were probably asking because when we did a 4-term polynomial, we factored in pairs. So what I told them was, at the time, you can't really factor by grouping in a 5-term polynomial unless you take 2 terms and stretch it out to 6 terms so you could pair some things off in a certain way. That's mostly the answer to that. But now we learned that there are some polynomials, like a quartic 5-term polynomial, for example, that using the rational root theorem, you can actually find a rational root first that would exist somewhere if it does. It doesn't always for quartics, but try and see if there are any rational roots within there. Now, if they are all complex solutions and it's a quartic, your hope is that, oh gosh, how would I say this? I don't know if I could answer that one. In some cases where it's all complex solutions, sometimes you have to have a root given to you. Otherwise, I don't really know what you can do to it. But in a 5-term polynomial, you can use the rational root theorem on top of it. And if you don't know what that is, that's that P over Q testing. Try and find factors of your constant over factors of your leading coefficient and test and see which ones give you 0. And then you can at least find one of them to break it down into hopefully a cubic or quadratic or something that you can then factor with some way that you know how to. So I just wanted to bring that up. Factor by grouping may not be possible, but you can do more. Okay, now we're going to some of the new questions here. So let's see what we have in store for us. When we are dividing polynomials, how do we determine how to write the remainder? Okay, that's a good question because, with my kiddos, what I tend to do, what I started to do, and if you saw any of my solution guide videos where we started was, when we started long division and synthetic division, I said, to make sure that you're doing it right, I want to give you problems that have zero remainder, that have a zero remainder, that have no remainder, so that if you get zero, you did it right. If you get a remainder, if every problem has a remainder, and even if you get a remainder for your answer, it might not be the right remainder, and you might not know whether you're getting it right. So anyway, the whole point of that was we didn't practice a lot of remainder stuff, but our review had some remainder stuff, and you can expect remainders to come down along the way. Now, I don't actually have a division problem with myself right now, but let's say we did divide something. We divided by right there and do some work, and then you get a remainder of 7. Right? And let's say your equation was x cubed minus 3x squared plus 6x minus 1, like that. So, and your remainder was 7. Here's how you write it. Oh, by the way, here, it has to divide by something. Let's say we divided by x plus 4. Okay. So this quotient ends up being this guy right here. So it equals x cubed minus 3x squared plus 6x plus 1. And then you don't just write remainder 7, right? The 7 means 7, your x plus 4 couldn't divide into 7 at all. And that makes sense because this has a term that is 1 degree larger than the constant. But it's still, this 7 is still dividing by that whole, right? It's still plus 7 over x plus 4. Okay. It's like if I did 7 divided by 2. If I did 7 divided by 2 with you guys and asked what that was. Well, it's 3 with a remainder of 1. But how we could also say that is it is 3 plus 1 over 2, right? It's 3.5. But that's how that thing's working right there. It's 1 out of that whole of 2 given that remainder. So that's how you write it if you have the remainder there. Now, if it's a negative 7, then you would probably put a minus right there. That's how I would probably go at it. Oh, sorry. So I hope that answers that. But that's also, I just wanted to lead into the fact that, yeah, we haven't done much with remainders, but that's how it would look. Okay. Good question. All right, next question here. Can you do a quick summary type explanation of completing the square? Yeah. Now, one of those things where I'd love to point to an older video at some point, maybe for you as well, if I could. And it covers it, so it covers it maybe in greater detail. So I'll try and stay short with it. Let's first talk about objective of completing the square, overall objective. When you have something, and I'll write an example out to kind of get it started. Plus 10x minus 2 like this equals 0. Okay, let's say we wanted to solve this. Now, it's not factorable, and we could use quadratic formula. There's something called completing the square as well. See, if we could factor this, what we would do, when we say not factorable, we mean when set equal to 0, there's no product right here I could make equal to 0. Because if I have a product equal to 0, I could use zero product property and say this or this equals 0 and solve. Completing the square doesn't need to be set equal to 0. The objective of completing the square is to create what's called a perfect square trinomial, not these terms, not this specifically, so that you could factor down to a squared quantity. And it can equal anything over here. It can equal whatever. It doesn't have to equal 0. Because in a product equal to 0, it's two unknowns that multiply to 0. One of them has to be 0 in that case. This thing, when we square it to become whatever, it's the same number twice, so you get to take the square root of both sides. So the objective of completing the square is create a perfect square trinomial that can factor down to a squared quantity, so you can take the square root of both sides. Now, what's the process? The process is, given a 1x squared, and I say that loosely because there are some teachers that can go like, get any perfect square value. Get a 4, get a 9. I say go with the 1, complete the 1 square, and we're going to make things easier for ourselves. Given a 1x squared right here, and ideally an even number right here, use these two terms and say, okay, there are a bunch of x plus somethings squared that can work out and expand out to something like this. Only because of this 10 specifically, there's only one specific number that could go here to make that. And I think a lot of people know what it is. What number plus itself is 10. We get the picture. But the idea is to make that perfect square trinomial, we need a different constant. This -2 right here is not the value that's going to do it. So instead we say, hey, this 2's got to move over in the equation because we got to come up with another term there, right? So we come up with our own. We're saying, all right, we got to add something new here. Now there's a 2 on this side, and of course, like I added 2 on both sides, whatever you add to one side here, we're going to add to the other side here. So we say we're going to come up with something new. And there's only one thing, there's only one value here specifically that gives us a perfect square trinomial. The number that times itself gives us this and plus itself gives us this. So if something doubles to get this and squares itself to get this, then this must be half of this number, and this must be the square root of that number. So to get this number, we take half of this number to get that, and then square it to get that. You know what I mean? Half of 10 is 5. 5 is the number that technically goes here. We'll get to that. But half of 10 is 5. 5 squared is 25. X squared plus 10x plus 25 is a perfect square trinomial. It factors down into this thing right here. Now you might wonder, why did I have to come up with a 25 if I know it's just going to be a 5 here? Because you got to add 25 on this side as well. You add one thing to one side and one thing to the other. And 2 plus 25 is 27. So we've come up with this strategy here where we've built a perfect square trinomial, factored it down to something squared, and its benefit is we can now take the square root of both sides, and that allows us to solve for x. Even though there were no rational solutions, it wasn't factorable. Square root of both sides, x plus 5 is plus or minus 3 root 3. Subtract 5, x is negative 5 plus or minus 3 root 3. The idea is two solutions there, two irrationals, or imaginaries, or whatever we'd come up with. And we could do that now in that way. So completing the square is take half with a 1x squared. I'm just going to say it specifically. It's got to be a 1x squared for what I'm going to do. Divide this number by 2, your linear coefficient, and square it. Now, why did I say ideally an even number? Because if it was an odd number, dividing by 2 leaves you with a fraction. So if I had x squared plus 9x minus 4 equals 0, and I add the 4 over, x squared plus 9x plus blank, 9 divided by 2 is 9 halves. And 9 halves squared is 81 over 4. Well, the problem is now you got to work with a fraction, and do 4 plus 81 over 4 right here. You know, and then you got to get a common denominator and then take square root and such. And it's just not as fun to deal with. So I said ideally there, I'd probably just use quadratic formula, which has a fraction embedded within, but we don't have to compute things with that fraction, except for maybe reducing it. But no common denominator, not have to square it later, all that kind of stuff. So I hope that that answers it in a good nutshell. That's probably longer. Whoopsie, I don't want to do that. That's probably longer than my actual summary that I had before. Okay, how many tests will be there until the midterm? Not a content-based question. I don't know what a midterm is. If you mean the December final, not counting pre-test, just unit tests, I think 4. 4 units, 4 tests. Quizzes in between, pre-tests for every test. Moving on. I had softball practice stuff tonight. I'm very thirsty. Is there an easier way to solve an equation using Pascal's triangle? For example, any shortcuts or faster ways of solving it? Pascal's triangle is the shortcut. If I asked, and I don't know if I want to do the whole thing here, if I'll keep the number small, let's just do x plus 2. If I did x plus 2 to the 7th power, the long way would be take 7x plus 2s and multiply them out. And remember, you kind of have to do one at a time. In one kind of way, I can kind of do 3 or 6 at a time and leave the last one over. Because here's the thing, you don't just do x times x times x plus 2 times 2 times 2 like that, right? You can FOIL this part out, right? X has to multiply with every one of these things here, and 2 has to multiply with every one of these. You'd keep going. But I could do perfect square trinomial, x squared plus 4x plus 4 at least there, get another set and call this x squared plus 4x plus 4, and this x squared plus 4x plus 4, and then I have x plus 2, and then I got to multiply this 3 by 3 and get 9 terms to combine, and then multiply by that trinomial, and then that binomial there. That's going to take a long time. Pascal's triangle cuts through a lot of that. There's still a lot of work to do, and listen, the numbers are big. No matter what you do, the numbers will be big. Pascal's triangle is the shortcut. The idea of Pascal's triangle is that those coefficients are how many of that degree add together and fuse it together, given that row that we're talking about. So Pascal's triangle, once again, is row 0, row 1, row 2, row 3. We're adding the 2 numbers above it to get the next one. Row 4, row 5, row 6, and then row 7. 21, 7, and 1. So row 7, there will be 8 terms in this thing, and our terms here will multiply by these guys here. Now, how fast will this go? I built the triangle in whatever seconds. I don't have much room here. But if you recall, you multiply this number by this to the 7th times this to the 0, plus this number times this to the 6th times this to the 1st, plus this number times this to the 5th times this squared, like that. So the first one's going to be 1x to the 7th to the 0, plus 7x to the 6th times 2 to the 1st, plus 21 times x to the 5th. Thankfully, these numbers are small, times 2 squared. I could probably leave that. Plus, 35 times x to the 4th times 2 cubed, plus 35 times x to the third times 2 to the fourth plus 21 times x squared times 2 to the fifth plus, just another times 2, 7 times x times 2 to the sixth plus 2 to the seventh. Now all I have to do is multiply 7 by 2, 20, so 14, 84, 280. I can't do that one really fast. And blah, 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 right? And then I'm done. I'm done. That's fast. That's fast. This thing here, And look, this number could have been bigger. It could have been to the 10th power. Some of the smaller ones, obviously squared is, I know to do that one kind of faster with that method. It used Pascal's triangle though, right? Square that number, double that, and square that. So it's all within. Pascal's triangle is the speedy way. And honestly, what I should mention here is Pascal's triangle isn't as important for, let me bring this back. Pascal's triangle is mostly used in probability and statistics. And the most important thing about Pascal's triangle is actually getting an exact value. So maybe this exact one right here down the line. But expanding it, it's kind of a cool, neat feature you can do for a lot of things over and over. But so Pascal's triangle is best used for that within that binomial expansion. Okay, good question. Do you have to make up quizzes if you miss them? Well, again, not content-based. Let me say you can't make up quizzes if you miss them. If you miss it, that was your shot. Get a 0 until you take your test, and then your test score replaces your quiz score. Make your quiz days. Don't be sick. I know COVID can be an issue, but outside of that, make class. Try. When factoring, why can you factor x squared minus 1 further, but you can't factor x squared plus 1 any further? Technically, you can. They just aren't rational. When we say something's not factorable, we're saying that there are no integer, I'm erasing, that there are no integer values that don't work with it. So x squared minus 1 factors to x minus 1 times x plus 1, and that's a difference. Whoops, we don't need parentheses. That's a difference of two squares, right? And then we say, oh, but you can't do x squared plus 1. Well, you can, just those numbers aren't integers. They are imaginary numbers. It's actually x minus I times x plus I. See, check this out. X minus I times x plus I. Well, we know the whole difference of two squares thing, right? It's a squared minus b squared. I squared is -1, and that gets you x squared plus 1. So it does work, right? It is there. So, but your real question may be within, why can't you do it in the way that we're expecting with integers and stuff like that? Well, a quadratic is too small in that its factorization has to be just x's, means the most that you can add to it is just one more term. And then given that these are positives right here, the only way for that to form is from two positives or two negatives, or what, because a negative times a negative is still a positive, but that would always introduce another term along the way. See, with x squared minus 1, what happens is the middle term cancels out, right? Difference of two squareds comes from x squared plus 1x minus 1x minus 1. These two terms cancel by being opposite signs, and that comes from this opposite sign here and here. When you have pluses here, we're assuming every sign the same, like assume every term positive, like x plus 1 times x plus 1. But what happens is there's a middle term, plus 1x that combines, doesn't cancel, and those come together. So you get a new term introduced. There was no middle term that canceled out. Once you get a sum in difference of two cubes, the sum of two cubes exists because in a cubic, there's enough wiggle room to have a binomial times a trinomial. And in that trinomial, you can have a negative term. We talk about a cubed plus b cubed equaling a plus b here, but not everything here is positive. It's a squared minus ab plus b squared. Yeah, we have enough things to keep these guys positive here, but middle terms cancel. A times negative ab is negative a squared b. B times a squared b is b times a squared is positive a squared b. They cancel. And then that's where you get those things right there, right? Everything else is there. So there's a middle term that can be used because there are enough terms in a trinomial from a cubic factorization that we can introduce a negative that throws off everything else and keeps everything else positive. A times a cubed. I can't speak. A times a squared is a cubed. B times b squared is b cubed. So the answer is it can factor, right? But not in the way we want to. Just like x squared minus 11. X squared minus 11, we say that's not a difference of two squares. Sure it is. X minus root 11 times x plus root 11. But when we factor, we're talking about integer factorization, right? We're not talking about irrationals and imaginaries. And same thing here. We can factor x squared plus 1 as the sum of two squares. They're just not even real numbers like that. All right, can you please go over synthetic division? again, can you please go over synthetic division again? It was confusing at first. If you're asking process versus reason, let's just talk process on it. Let's do a problem and talk process on it. But synthetic division, remember, it's not like real division, right? It is synthetic, right? Artificial. It's a way, whoever invented it was pretty genius with it as far as saying, let's cut through the things that we don't need as long as we set it up right, right? We take out x's, we take out subtraction, knowing that we are going to have a linear factor with a 1 coefficient, or we'll create that for ourselves when we factor. Knowing that we are going to be writing something in standard form in descending order of degree, and any degree that's missing we got to place as 0. And noting that our final result will be 1 degree less than our other one. So it's cutting through a lot of things and it's assuming a lot of things out of it. But the main reason is because we do that kind of division a lot for polynomials. So what's happening here is, we can't do synthetic division ideally on a problem like x cubed, I'm making this up, minus 2x squared plus 3x plus 7 divided by, x squared plus x plus 2. We can't do it here because this is a quadratic. Your root, if you could come up with 2 roots, which we can't really in this way, but if you can come up with 2 roots here, good integer roots, then you could do it twice. Once on one part and once on the other part. But we have to do it on a linear factor with a leading coefficient of 1, a 1x minus 4, something like that. And hey, let's just do it here. If we get a remainder here, let's put an 8. Maybe there's a chance it'll work here. Let's just do this right there. Okay, so here's what happens. Synthetic division, again, takes out the variables and takes out subtraction. It lets us do addition. How does it let us do addition instead of subtraction? Because the way negative 4 ends up multiplying by numbers in long division to subtract, we get to use a 4 in its place. 4 represents the root meaning the value of x that would give you 0 in this situation. We use the root there, opposite sign, which means we get to add the results of these things. I'm not going to get into the why of the matter. Let's talk about the how of the matter. Given that this is a cubic quadrinomial, we go degree 3, 2, 1, and 0. We have to write these all the way down to degree 0, to the constant, with our coefficients. 1 x cubed minus 2 x squared plus 3x plus 8. If this 3x was not here, like that, you'd have a 0 in its place. But we're going to have a 3 because that's what I made up. And I don't know if this will work right. And if there's a remainder, that's fine. Here's the idea. There's another row right here where we're going to add these numbers with these numbers. And again, I'm not going to get into the y, but 1's not adding with anything right now. This is just the 1. Besides the fact that x cubed divided by x is 1x squared. That's the only y I'm going to talk about. This root, that part of the negative 4, it has to do with the negative 4 here with long division, but this 4 is going to multiply by that 1 right there. So times 4 right there. Again, making up an example for you. And we get 8. We add these together. Negative 2 plus 8. Instead of subtracting a negative 8, we add a positive 8. We get a 6 there. This will have a huge remainder. Times 4. 6 times 4 is 24. So 24 goes here. 3 plus 24 is 27. 27 times 4 is 108. And 108 plus 8 is 116. All right, whatever. And 116 is a remainder. What happened is we went from a cubic to a quadratic. We went from a quadratic to a linear to a constant, and constant to remainder. So your result of dividing these is x squared plus 6x plus 27 with a remainder of 116 out of x minus 4. Again, just the idea is add the row. And listen, when we do notes, the success criteria states these things pretty straight up. Identify your root here. Opposite sign, it's the thing where you set equal to 0. And place that in this corner right here just to have it visually. You are going to add the first row with the second row right here, and each subsequent value comes from multiplying here from that portion before. That's all. I mean, that's the process. If you want the why of the matter, I have video stuff that connects an actual long division problem with a synthetic division problem. It says this is where the x is cut out, this is why the signs switch, this is why they add, this is where it does it. But you need this to be a 1, and if it wasn't right here, now suddenly your root is 4/3. Whoops, 4/3 like that. And then you need to place a 4/3 there, and then you need to divide your result by 3 at the end. So it's kind of difficult when you do all that. Okay, so there's that, to me, that quickly going over in that way. Okay, when dividing a polynomial synthetically, whoops, I lost it. Does the value 0 change signs when boxed off? For example, x equals 3 is the same as x plus 3. I need to read that again. I'm going to erase this in case I have to write something. Let me read that again. When dividing polynomials synthetically, does the value 0 change signs when boxed off? Are you saying if 0 is your root? Oh, I don't know what's being asked. Does the value 0 change signs? Oh, maybe you're not actually talking about the number 0. Okay, I hope I'm answering it correctly. Are you calling x equals 3 the 0 like a root? Like a 0 is a root? If so, I just answered it kind of in the last one as I did a synthetic division problem. If you're dividing, it depends on how we're doing synthetic division. If they're asking you to divide and we're dividing by x plus 3, then the root or the 0 or the root is x equals negative 3, because it's all about what value of x gives you 0 in x plus 3 equals 0. It's x equals negative 3. So that sign changes, if that's what you're asking. If you're asking if x equals 0 is your root, do you change the sign of 0 to negative 0? I don't really know if that's what you're asking. Two things to that. No, 0 is neither positive nor negative, if that's the question. Number one. Number two, if x equals 0 is your root, then x is your factor. Dividing by x means factoring out an x. You don't have to use synthetic division for that. You can just straight up do it. Just take x out of all your terms and you're good. If you're talking about this one right here, yes, they do change sign. But, because you said x equals 3 is the same as x plus 3. No. X equals 3 is the root or the 0. X minus 3 is the factor that we're dividing by, right? So anyway, I hope I answered it. I don't really know whether I did. But if it was 3x plus 4 as your factor, your root isn't negative 4. It's negative 4/3, right? Subtract 4 divided by 3. But yeah, the sign changes because how you set it on the other side of the equation. Okay, let's see how long we've gone. 26 minutes, pretty good for a power hour. I don't know how many questions are left. Just a few. Several. Can you do synthetic division if the number you're dividing by has a variable? Well, technically, when we divide, and I like all these synthetic division questions are in a row here. Technically, when we do divide, I made up a problem before. I'll just x squared plus 2x plus 7 over x minus 1. Technically, when you divide, you are dividing by something with a variable like this. When you write it out in synthetic division, you are just writing out the root. So if you're asking, could I put a variable inside of here? No, synthetic division cuts out variable aspects of it. It's taking those parts away and saying, these are the only parts that are relevant to our answer in our quotient, because the other parts subtract and cancel out, and you wrote everything in a systematic way that they go down in degree and yada, yada, yada. No, there's no x that's involved there. You can have an imaginary value, though. This could be something like 2i, which actually showed up on our pretest right there. And yes, that could happen, in which case, I'm not going to do a whole problem, but if I had like a 1 and negative 3, a 1, a 2, and a 7, here, let's say this. Let's say we divided by x minus 2i. X minus 2i, we could have a 1, a 2, and a 7 here. Probably just going to be a remainder because everything's positive. That's okay. You add the 1 here, multiply by 2i, you get 2i. This is 2 plus 2i. Multiply both these by 2i, you distribute, you get 4i right here. And 2i times 2i is 4i squared, which is negative 4. 4i minus 4, add those, you get 3 plus 4i. So you can have imaginaries in there, some complex things like that, and suddenly this is now x squared. Actually, not x squared, that's the linear. Now you have x plus, and then this constant 2 plus 2i, and then here's your remainder, 3 plus 4i all over x minus 2i, yada, 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 yada. You wouldn't even want an imaginary in the denominator because it's not rational suddenly. You'd have to multiply by its conjugate and all this stuff. But no, variables wouldn't show up in there. Variables get weeded out in synthetic division. That's the point. And technically, when you're dividing, you're not just dividing by 1. You're dividing by x minus 1. You know what I mean? We just write the root in the diagram, but we're dividing by the whole factor. Okay, next question. Why does the quadratic formula work? And why does the discriminant tell how many real solutions there are? I know why it does, but why is it specifically b squared minus 4ac? Okay, there are two questions in this. Why does it work? I think you're asking, why is that the formula? You know what I mean? Like why is it specifically this? Who made this up and said, this works? It's because the formula came from the condition. The initial condition is ax squared plus bx plus c equals 0. They're saying solve for x. See, this generally, actually, before I solve this, let's say it just said ax plus b equals 0. And I said, hey guys, solve for x here. what would you do? You would subtract b, and then you'd divide by a. X equals negative b over a. That's great, right? We get x by itself in kind of one step. You could isolate the x term before you divide. Here we have two x's within that. You can't isolate them, you can't combine them, so it's a little harder to do. Now, I'll do the quick proof for you. I'll say, here's how we get from this to the very end. That's fine. I'll be fast, though. I'm just going to say, hey, just accept that it works and move on, unless you can catch up with me or pause and write it down. You solve it by completing the square, right? Completing the square is your savior, guys. If you like quadratic formula more than completing the square, and there are parts where there's more ideal, I get it, that's fine. But have respect for completing the square. It's why quadratic formula exists in the first place. So here's what we can do. We can move the c over, factor out this a because we need a 1x squared. That means this becomes b over a right there. And we need to add something in here that makes a perfect square trinomial and add the same thing out here. It's going to multiply by a. Again, I'm not assuming you understand any of this. I'm just going to do it. B over a over 2 is 1/2 of that, so b over 2a. Squared is b squared over 4a squared. So we're going to add that to both sides, b squared over 4a squared. And I have an a over a squared, which becomes b squared over 4a like that. Now, if I want to combine like terms, or not combine like terms, if I want to get a common denominator, I should multiply negative c by 4a over 4a. So I'll have negative 4ac up top right there. This factors down to x plus b over 2a quantity squared, right? Whatever half of this is what goes inside there. This was that negative 4ac, like I said, and there's the b squared right there. And this is all over 4a, like that. If I divide both sides by a, which is also multiplying by 1 over a, like that, then this will have a 4a squared over here. So I'll have x plus b over 2a squared equals, I'm going to rewrite these to b squared minus 4ac, of course, because that's what we see in the formula as well, over 4a squared like that. I take the square root of both sides, and in doing so, take the square root of both the top and bottom. You know what I mean? The whole thing like that. Now, when we take the square root of something with an x in it, we can't assume that the thing we squared would have been positive, so we have to include a plus or minus. So x plus b over 2a equals plus or minus the square root of b squared minus 4ac over the square root of 4a squared. Square root of 4 is 2, square root of a squared is a, so that's over 2a. And subtract the negative b over 2a, you get x equals negative b over 2a plus or minus the square root of b squared minus 4ac over 2a. And that's a common denominator, so you get x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. All over 2a. So boom. There's the formula, right? And it comes with a proof, right? So why is the formula the way it is? Because we're solving a quadratic in standard form set equal to 0, and that is what x is in that scenario. It is through completing the square that you actually get that thing. But we specialized it, and we weeded it out, and we wrote it in such a way that said, hey, x is now by itself. You get to plug in the numbers. It's a good question there. All right, yet another part of this. The next question was what? Where is it? Hold on. Why does the discriminant tell how many real solutions there are? I know why it does. Why is it specifically? Okay, before I answer your little question, let me just state for those who don't know. Yeah, the discriminant inside, if this number is positive, then you have 2 real solutions. If it's a perfect square, there are 2 rational solutions. If it's a non-perfect square, there are 2 irrational solutions. If the number is 0, then you have 1 real solution with a multiplicity of 2, if you guys remember what we were talking about there. And if it's negative, you have no real solutions. And they're saying they know why that is. Yeah, if it's positive, you take the square root of a positive number, you get a positive number. Rational, irrational, you're adding or subtracting a positive number, you get real solutions. If it's 0, the square root of 0 is 0, and adding or subtracting 0 means you're not adding or subtracting anything. Your only answer is negative b over 2a. And if it's negative, you're taking the square root of a negative number. You get i's, that's why they're complex. Their question is, why is it specifically b squared minus 4ac? Same reason for your first question, why the formula is. It's the completing the square proof. It's just within the thing that it just so happens to be, right? So that's the idea. Why? And then the square root tells you how many real solutions. But why is it specifically that? Because that's just how the formula works out, right? And so if you take the square root of a negative, suddenly it's imaginary numbers. So anyway, that's the idea. Okay, good question within, and I hope that it wasn't too long that I went to prove that. And of course, you're just watching what you want to watch, and I hope that was kind of interesting how you saw that. Okay, how do you find irrational roots of a quartic polynomial when given 1 irrational root and all the other roots are irrational? Why specifically a quartic? Well, you said irrational. So, again, if I make one, well, I can't make one up because I'd have to actually come up with like something that actually is a root. I could find one online, but like I'll make one up and not actually do it. So you're saying, let's say I had x to the fourth. I don't want red. Let's say I had x to the fourth minus 6x cubed plus 9x squared minus 27, whatever. And then you're saying, okay, here is, wait, what did you want? How do you find all the roots? So let's say I said find all the root, solve for x, right? Solve for x. Wait, I'm missing not missing, but let's go plus 36, whatever. I don't know if it's gonna, whatever. And I go, okay, because I don't know what the things are. And we're like, okay, solve this thing. And it's very, by the way, it's very, just as you said, all the other roots are irrational, right? So it's very possible that there are no rational solutions here. They could come in conjugate pairs of irrationals and imaginary. In fact, is this question because of the bonus question? The bonus question actually had imaginary numbers, but I see why you're asking a different one. It's the same idea. Let's say I gave you a root and I said, oh, okay, by the way, one of the roots is the square root of 6. I don't know if that works or not. All right, how do you find them? Because they could all be irrational, right? So how does this help you find it? The best way to do it is remember that because these have all rational coefficients right here, that means that if root 6, the square root of 6 is one of your zeros, is one of your roots of the thing, then so is negative root 6. How does that help you? Because that means that x minus root 6 is a factor and x plus root 6 is a factor. And if we expand this into x squared minus 6 like that, then we could divide this by x squared minus 6 and use not synthetic division, but long division on that thing. Use long division on this because it's a quadratic, and then it breaks down to another quadratic for you that you can solve using quadratic formula completing the square. Couldn't solve by factoring if they're irrational roots, so that's what you would do. Come up with its conjugate, expand out this polynomial into something like that right there, and then divide it using long division. You could use synthetic with root 6 and negative root 6, one and then the other. I wouldn't recommend it. There's a lot of combining and stuff. Same thing is true if this was 6i and negative. If they said 6i was your root, then you use negative 6i as the root, and then you have x plus 6i, x minus 6i as a difference of two squares there. It actually becomes a sum of two squares. It becomes x squared plus 36. And then you divide this by x squared plus 36, long division. Get that started, and then continue forward and try and find your other roots. I don't know if those answers would work. You can try it for yourself. But if you find one online that's like that, that's how you'd go about it there. Good question. That's how the bonus question on the pretest worked. Can you review all the ways to factor that we learned? Let me see if I can kind of recall them all. Whoopsie. So the different ones here. Main one to listen, do not gloss over this one. First one is greatest common factor. Whether it's numbers or variables or both, greatest common factor. You always find these first. Always, always, always. Number one, they have to be factored out. Period. It's a part of it. It has to be factored out ultimately. If you don't find them first, you made your numbers bigger. Here's the number two. Your numbers are still bigger, or they're not representative of that perfect cube or perfect square value that you're looking for, and you're working really hard to come up with it because you never found the GCF, and then at the end, when you said, whoo, I'm factoring all done, there was a GCF you never took care of in the end. And that's really important. So greatest common factors first, whether they're numbers or variables, that's the first one. Then we started talking about, I was about to say greatest common factors again, factoring when your a value is 1. So let me write examples of all these things here. Let's say we had a 2x cubed plus 6x squared plus 8x here. So you can factor out this 2x right here, and then you're left with x squared plus 3x plus 4, right? And that's not factorable, but whatever. You know what I mean. A equals 1, factoring those, where you have some sort of like x squared minus 6x minus 40, like that. And so this kind of factoring was, because these are just both x and x, that means that the two middle terms that combine are just multiplying by a 1 here. So whatever these numbers are, do also add to those, but they're factors of 40 that you're looking for. So in this case, it would be negative 10 and positive 4, like that. Negative 10 plus 4 is negative 6. Negative 10 minus times 4 is negative 40. By the way, let me just mention this really fast. This has nothing to do with your question, really. But people are factoring this. If your thing was asking you to factor, and it was an expression where f of x equals, don't write x equals 10 and x equals negative 4. This isn't set equal to 0. That's zero product property. We're not solving anything. We're factoring. You're done right here. Don't keep solving. We're not comparing to anything, right? So just, be careful on that. Not the person who asked, just in general. A is greater than 1. A is greater than 1. Let's do, let me kind of come up with one. Okay, let's do this. Let's do 4x squared minus 19x plus 12. So something like that. The idea here is that, so no GCF, by the way, always look for GCFs. No greatest common factor here to start with. This could either be 4x times x or 2x times 2x. It won't be 2x's because then they'd multiply with some values here and add together to make even numbers here, and 19 is an odd number. So it's got to be a 4x times x. We know it's a negative and negative. I'm not saying how you do all these, but these are the kinds that we have. 12 factors of 12 are 12 and 1, 6 and 2, 3 and 4. Can't be 6 and 2 for the same even odd stuff we talked about. So it's either 1 and 12 or 3 and 4, and it has to be this way because you can't put a 12 or 4 in here and be a GCF with 4. So 4 times 12 is too big. 4 times 4 is 16. 3 times 1 is 3. Negative. So negative 16 minus 3 is negative 19. So it would be minus 3 minus 4. A lot of those strategies work out a little faster for yourself if you know what you're doing with them. But anyway, that kind of factoring is involved. I think that's what you were asking about. Then we had some special case factoring. We had a perfect squared trinomial and difference of two squares. I don't think I can fit everything here at the same time. We could have 49x squared minus or plus 70x plus 25, for example. And you say, hey, this is a perfect square, right? We're squaring 7. And then this is 5 squared. And is this number double 7 times 5? 7 times 5 is 35. Double to 70. Yes, it is. That makes this 7x plus 5 quantity squared, right? That's just like kind of one idea of that. And then difference of two squares. I've kind of written a bunch of those already right now. But if we had 49x squared minus 25, for example, I don't need parentheses. If you had 49x squared minus 25, you realize, hey, two terms, no GCF right here, including x's, perfect squares right there, and that difference. That should really call your attention that you see that. And honestly, I think this would to you. When it doesn't call to people's attention is when it's x squared minus 1, because people don't think of 1 as a perfect square, or x squared just shows up so often that it doesn't resonate. Anyway, this would be 7x minus 5 times 7x plus 5, for the reason that the middle terms cancel out. I mentioned that kind of a bit ago. So there were some right there. And then we started looking at some cubics. We had the sum of two cubes, and difference of two cubes. I'll just write them kind of as one thing. I'm not going to write examples really right now, but just that a cubed plus b cubed. And honestly, I should have been doing this for these guys. A cubed plus b cubed is a plus b times a squared minus ab plus b squared. And then a cubed minus b cubed is a minus b times a squared plus ab plus b squared, like that. And as long as this is a quadratic, you can't factor down any deeper. We had factoring by grouping. Now, factoring by grouping is something that you always want to look at when you have those cubic quadrinomials or any sort of quadrinomial there, and just kind of ask yourself, proportionately, are numbers able to kind of factor out because of, is there a proportionality where one number is like that many times larger than the other? If I had something like, let's say like 2x cubed plus, let's do 6x squared. Notice how 6 is 3 times larger than 2. And then check on like this one. It was like minus 10x minus 30. Factoring this right here. Notice how 30 is 3 times larger than 10, or negative 30, 3 times larger than negative 10. As long as everything else kind of works the same way, going down a degree, the signs are, going to work the way there, then you can factor by grouping. And it's something that calls to my attention immediately. I'm really big on proportions that way. So you can factor a 2x squared from here and you get x plus 3. You factor a negative 10, you get x plus 3. And x plus 3 is a common factor in both of these. So then you get, and by the way, there was a GCF here of 2. I made up the problem, so I wasn't paying attention to that. So I have 2x squared minus 10 times x plus 3. And yeah, there is a GCF still there of 2. A lot of people miss it. So factor out the 2, you get x squared minus 5 times x plus 3, yada, yada. So those are a lot of them right there. The only other factoring that we really looked at after that was using rational root theorem. Using rational root theorem. So I'll just write that RRT, last one, rational root theorem, which was all about getting your P's over Q's, right? Factors of your constant divided by factors of your leading coefficient. Let's do 2x cubed. I just need to make sure my last number works. Plus x squared, let's minus 13x plus, I think 6 will work there. If I work my p over q values out, and again, I won't get deep into the why, we've done it before, but the idea is factors of this number are 1, 2, 3, and 6, and you divide them by factors of this number here, 1 and 2. 1, 2, 3, and 6 divided by 1, 1, 2, 3, and 6 divided by 2. Those numbers are 1, plus or minus 1, 2, 3, and 6. And then you divide 1 by 2. 2 divided by 2 is 1, we already have that. Divide 3 by 2. And 6 divided by 2 is 3. We already have that right here. So these are your possible roots here. One of these will give you a 0. One of these will give you a 0 for your thing. At least one of them. The other might be imaginary conjugate pairs, whatever. But when we use synthetic division to divide that out, then that factor remains with whatever you got as your quotient. So you come up with, what number would play here. 1 wouldn't work. It's 2 plus 1 minus 13 plus 6. -1, you give a shot. I don't think that's going to be much doing for you as well. Try 2. 8 is 16 plus 4 is a 22. Minus 26, no, plus 6, it doesn't work. But anyway, you keep trying it until you find your 0. Let's say, and I had the number in my head. I forget what it was suddenly, but one of these numbers has to work here. And then when you find your actual value with it, then you use your synthetic division. Let's say it was -2, right? That means you're dividing this, or you're factoring out the x plus 2, and then whatever remains in synthetic division from this thing right here, then you go forward on that thing. You get a remainder of 0, whatever remains here, the x squared minus 6x plus 8, whatever it is. And then if there's more factoring down the line here that you can do, you do. Oh, there's one more that I missed. It was the whole, the quartic and quadratic form. Quartic and quadratic form, or not a quartic, it could be an octic, it could be a sextic, something like that. But if you have some sort of x to the 4th minus 12x squared plus 20, like this. It's like a quadratic, as if it was u squared minus 12u plus 20, like that. And then you're saying, like, okay, that's u minus 10 and u minus 2. But, it was originally x to the 4th x squared. U seems to take place of x squared, so it's x squared minus 10 times x squared minus 2. That's the breakdown. You don't need the u's. I'm saying it's like that, as in its quadratic form. These things go down by even degrees to the constant. And maybe this perception helps you a little bit, but that would end up being the factoring. And really the big part about all the factoring I talked about right now is sometimes you do more than just one bit of factoring. Maybe you start with a GCF, and then it's the sum of 2 cubes, and then that has a difference of 2 squares, or this quartic kind of thing, right? You keep breaking down until you have the essential as factored as you can get, right? That's the idea of those things. Okay, so that was the list of all of them that I can think about off the top of my head right there. 4 more questions. Living up to power hour name, 48 minutes. When doing long division with letters, how do I divide an r cubed minus 4 to an r to the 5th or something like that? Well, they all have letters. At least not the actual long division stuff. Our whole idea of long division, and again, go to your success criteria to help yourselves out in your notes. What it spells out is what we do here. But let's say we had some r to the 5th, and then r cubed, what'd you say, minus 4? Minus 4 right here. And I hope you're saying this divided by this, because the other way it doesn't go into it. You wouldn't divide it. R cubed goes into r to the 5th r squared times. Now what I did was I looked at the leading term here, and we're going to start talking about this when we start graphing polynomials. The leading term, first of all, you got to be in standard form. The leading term, the highest degree term, is the most dominant one. And what I mean by dominance is it takes hold in the long run, and it matters the most with respect to your problem. You'll notice this when we start graphing later, that a cubic has this specific nature to it, no matter what other coefficients you have, that it will have this end behavior of up and down, things like that, because of what that term is doing with it, coefficient and all. So we're only looking to see how many times this goes into the leading term in that portion of it. And then you multiply both of these two things by this, because the -4 matters for the difference, for what you're taking out of there. but r cubed times r squared is r to the fifth, right? Negative 4 times r squared is negative 4r squared. And then you subtract those results. And again, subtraction means subtracting a negative is addition. But you got to find it if there was an 8r squared right here, subtracting the negatives 12r squared while these cancel out. And then you see how many times r cubed goes into 12r squared. It does not, so that's your remainder. But you're always looking at how many times this goes into the leading term of the thing, right? That's the idea. I don't know if that kind of answers your question there. I'm not doing a full one. I've done plenty of examples of them, but that's what you're looking at, leading terms. And I don't know if you had a specific one in mind. You started one. That's kind of as best as I can say. Can you re-explain dividing polynomials, specifically long division of polynomials and alternatives to it? Well, I kind of started one just right there. Let me just undo and go back and say, when you set this thing up, when you set up your thing, you have your dividend, your divisor, and your quotient goes on top. The answer of the division is the quotient, by the way. But if they're asking you to factor something out of it, then have this portion times that portion involved. Okay. You are looking at, again, you need to be in standard form in these things. It must be standard form because it's all about dominant terms. How many times does the most dominant term here go to the most dominant term here? R cubed goes into r to the fifth, r squared times, as in r cubed times r squared is r to the fifth. Things like that. And then you take both of the terms, you take all the terms inside there to multiply and show up down here because these are what we subtract out of these guys right here. Like these go away, subtract the negative there, things like that. And then you rinse and repeat. How many times does this go into that? And so on and so forth. That's the idea. You go all the way until something like this, the cubic is larger than the quadratic, then this is a remainder, or until your remainder is 0. You would just keep going until then. But that's that idea. Now the synthetic division, I already explained in a different question, but synthetic division could not work with a problem like that because you need a linear factor to divide by. It would have to be an r minus 3 or whatever I said, not an r cubed. So you'd have to make sure to divide by something linear. So I did answer the synthetic division earlier. I'll leave it at that if that's okay. All right, 2 more questions. What part of the equation determines the maximum number of possible solutions in any polynomial equation? It's the it's the leading term of your polynomial. So that's the fundamental theorem of algebra that states if you have a 5th degree polynomial, that means you have an x to the 5th somewhere, right? Even if it's written out of order, that's your largest degree. In that, there are 5 solutions to it. They could come in conjugate pairs of 2 imaginary. They could be 2 irrational and irrational. There could be 4 rational, and then one of them has a multiplicity of 2, right? And the whole multiplicity of 2 means it's the same answer twice, x equals 1, x equals 1. It could be something like that, but it's the thing. If it was a 10th degree polynomial, there are 10 solutions to it. Any combination of real and imaginary, or rational, irrational, and complex, what have you, and multiplicities. But it's whatever the degree of your polynomial is. That's the rational root theorem in a nutshell. The fundamental theorem of algebra in a nutshell. And lastly, what do you do when you try and factor down something using the quadratic formula, but the exponents are greater than 2? When you say remember, quadratic formula is not for factoring, it's for solving. So if you're saying when you're trying to solve using quadratic formula, do you mean if you had a cubic and you used the quadratic formula, what would happen? Well, hold on. So if it said solve, now let's pretend for a second there are 3 terms because we're talking about a, b, and c, right? Solve x cubed minus 4x squared plus 7 equals 0. And you said, well, my a is 1, my b is negative 4, my c is 7. I say x equals negative b plus or minus the square root of whatever like that. Well, that wouldn't work because this isn't a quadratic. The quadratic formula is what it is. I think there's a cubic formula somewhere that's really never used. I would never use it. I don't know how to prove it and get to it. I'm not even going to try. And yeah, if it's 4 terms, where's the d involved there? Again, there might be a cubic formula somewhere. If you find the question a little bit ago, when you back up and find the question on why is the quadratic formula what it is or whatever, I prove it. The whole idea is the whole ax squared plus bx plus c equals 0, and we solve for x by completing the square. In a cubic, we're not completing the square. We're not solving. It's a different solution, right? It's a different solution here. No, you can't use it. So what happens when you use it? You get a wrong answer. And you don't factor using the quadratic formula. You solve, right? You're solving for values of x. I don't know if that's what you were asking, but yeah, don't use it. You can only, if you factor your cubic into a quadratic, right? If you factor into a linear times a quadratic, and you want to use it on that quadratic to solve those two solutions, go ahead. But you can't do it otherwise. All right, and that's it. That wraps it up. That's 55 minutes in, so that is our power hour. Thank you so much for watching, and I hope that these questions were worth your while here. If you have anything else, you can ask during class or in the comments or whatever it is you want to do. So thanks for watching Mr. Robinson's Q&A Power Hour. I plan on making a solution guide video at some point for my pre-test, and I will see you in that next one there. Take care.